Recording.
Good afternoon. Welcome to Cohort 17's SD&T presentation on fractals. Fractal geometry was introduced to the world in the 1970s by Benoit Mandelbrot, and we have discovered that it is integral to understanding our surroundings, from the smallest fungus to the atmosphere enveloping our entire planet.
Hello, me and my team are going to be covering fractals in nature. Fractals are repeating patterns that repeat the same patterns at different levels, and this helps us understand and answer questions in the world. One of the questions that help us answer is the coastline paradox.
Okay. Now, before understanding the coastline paradox, we must focus on iteration. Observing this topography, we can see that the ridges and shapes are reoccurring. Even though this reoccurrence may be happening over different amounts of time or different processes of erosion. Now let's zoom out of iteration into the faces of dimensions. Dimensions are usually looked at through scale, perception, and dimensions. Now we usually observe mountains on the dimensional scale between 2 and 3. Now imagine yourself to be an ant and observing a rock the same way that we observe the massiveness of Mount Rainier. Now observe yourself to be a 4-dimensional being and think of seeing Mount Rainier in the same way that we see its massiveness, but the same way that we observe a piece of paper. Now I would like to ask everybody a question. What is the exact coastline measurement of Norway? No, okay. Well, don't feel bad, because neither does the Congressional Research Institute, NOAA, or CIA, even though they were all measuring the same exact coastline. Coastlines can only be studied and observed through geometry, algebra, and fractals. According to the CIA, the length of the Norwegian coastline is 58,133 kilometers long. Now, if we were to stretch out this same coastline, it would approximately wrap around our world more than one time. In 1915, Lewis Fry Richardson discovered the coastline paradox, entailing that depending on your unit of measurement, the unit of the coastline will always be different. Now let's think of 2 parallel lines. One of those parallel lines being 150 yards and one of those parallel lines being 100 yards. Now add roughness, texture, and ridges to that 150-yard line. Maybe that 150-yard line, after adding to it, is going to come out shorter or approximately the same length as that 100-yard line. And we know this because of the coastline paradox. Now, Richardson found that if we are able to infinitely zoom into coastlines. Coastlines are always changing, and they are still always changing, and that change is being accelerated because of our hand in global warming, which is raising oceans and improving the power of erosion.
Erosions help us understand one of the biggest form of fractals, which is the river deltas. And this is the river delta in China. Help us understand that those kind of patterns are very similar to something that is within us. This kind of fractals are formed because of rainfall that falls down a mountain, and when erosion occurs, it creates a more deep depression, and then when a rain comes another time, that depression gets bigger, creating a channel that spreads all around the mountains and around the region. And this kind of pattern should be similar to us because it's very similar to our body. And another form is the spiral. You can see this in a hurricane. Another way you can see it is in a pine cone. It has the same kind of spiral formation, and also has the same kind of numbers that we're always going to see in nature, which is the number 13, which is one of the numbers in the Fibonacci sequences. I want you guys to see how it is and count how much is there.
Speaking of pine cones, I'll be talking about plants and trees. So, speaking of trees,
there has been, it's the most common example of showing fractals in trees. The reason why, because trees have little small branches showing the very similar of that of the big tree in the big picture. So the little branches will just like form into what makes it the tree. Like that. Here's a little example showing the tree, little animation showing how fractals are showing in the branches. Another example would be fungi. Fungi is a great example because you can see the stems of cells forming of the fungi, forming into the big image of fungi. Another great example would be fern. Ferns are a great example. If you guys ever been like that in a park or in an ecosystem with a bunch of trees, plants, you can see all those fractals. And that's a great example showing how every time you observe a fern, it will show little patterns so similar. So I encourage you guys to go to the park and just like walk around, look at the plants, look at the trees, hear the sound, and just observe it. Just see every fractal in the ecosystem.
Fractals in the frequency of vibrations. Dr. Emoto was a well-known Japanese scientist who populated the idea that molecules and water was shaped by certain humans' voices and sounds and thought patterns. In 1994, during an experiment, he began freezing water to notice that he began freezing water. And during the experiment in 1994, Emoto began freezing water and noticed that these crystals began forming through the sound waves. He couldn't have done his research without the help of a father of orchestra, Charlie. He's a German physicist who studied the differences of sound waves. And how he studied sound waves, where he used a metal plate. He used a violin bow to strum with a seesaw on top, which formed which took shape of the seesaw or the vibration of frequencies. And I have a video that demonstrates that. As you see here, there's certain hertz. The higher the hertz, the more frequencies you will see, like the more fractals, as you would say. You see 410 hertz, it begins to, there's 440 hertz. And these are limitless patterns that take place. The more salt you put on this platform, the more variations, and the higher the hertz, the more frequencies of shapes will take place.
Fractal sounds can occur naturally as well. Think back to the piece of wood that Rick showed us, where electricity was being used to demonstrate fractal patterns. These particular patterns are called Lichtenberg figures, and they were discovered, or named after the German physicist George Christoph Lichtenberg in 1777. He is the first to discover that branching pattern of electricity, which we now understand to be in a fractal pattern, and are found not only in electricity, but throughout much of nature, including our own bodies and these Chinese mountains you can see in the background here. Now think about the sound that a fractal strike will make. If lightning comes down, you have different fingers branching out into different further figures, all just demonstrating the self-similarity. And each of these is cracking a thunderbolt. This is a audio sonogram of a thunderbolt showing that fractal sound that is created from this Lichtenberg figure. Much of atmospheric phenomena requires fractal geometry to understand. We didn't understand that until the childhood of some people in this room. Sean Lovejoy was the first in 1982 to measure the fractal dimension of clouds. He looked at radar and satellite imagery and discovered that the edges were fractalized. And this pattern, in fact, repeats across scales. You see here a 1 millimeter demonstration of vortex in smoke, as well as a 10 millimeter picture of clouds, and then the circumference of our entire planet visible. And you see the similarity occurring throughout all these scales. Lovejoy's current work is focused on meteorological forecast. Our current deterministic figures only allow for prediction up to about 10 days, and this is the weather forecast. Lovejoy's work using a multifractal scaling approach generalizes the classic turbulence laws and discovers patterns from periods ranging from those 10 days through 30 years. His new models are being used to predict weather for years, decades, and to come, and to evaluate what we may expect in the next century. Understanding our future on this planet will require comprehension of fractal geometry. In Benoit Mandelbrot's book, The Fractal Geometry of Nature, the opening line is that clouds are not spheres, mountains are not cones,
Coastlines are not circles.
Branches are smooth.
Nor does lightning travel in a straight line. Understanding fractals help us understand that the world we live in is not as complicated as we think. They help us understand that the world has specific law to follow, and that help us understand and better understand our idea and help us become a better species in understanding in science, math, and art. Thank you for listening.
I've got a question for you guys. I like the presentation and the way that you presented how fractals work in natural environment. I have one question though, like is there any use that you guys figured out while you're researching about fractals? Do we use fractals in natural environment? Is there any specific thing that human beings use fractals for, like natural environment?
I believe our particular area of study was on this natural occurrence of fractals without any kind of human intervention. We'll be looking at human use of fractals in later Greece.
I did some research on fractals, how scientists use fractals, use trees to show how the CO2 goes into the trees and how that CO2 affects the atmosphere as a whole.
And I can also touch on that question. The first CGI is also going to be covered in another presentation. The first CGI that was used was actually done on accident, and it was because of a man pretty much trying to recreate mountains digitally, and that was what you've seen in like the first CGI moment of Star Trek. So that's the way that we use it. He did that through using fractals digitally.
Yeah, also by using fractals we can create different art and different beautiful art, because the Fibonacci sequence has numbers that show us that nature follows those numbers. Like the pinecone I showed you, it has 13 spirals, which is very common in our nature. And some artists like Leonardo da Vinci use that same concept to draw and keep doing this.
Further questions?